My name is Barry Dayton. My presentation will be representations of algebraic plane curves. Okay, so let's get started here. So we'll jump right to the advertisement. Okay, I have Wolfram Media has just published this book of mine. This actually came out this week, and I want to talk about it, or they want me to talk about it. There are various ways you can get this book. You can go to Wolfram Media, wolfram-media.com, or the shortcut here is wolfram.am Dayton curves. Get you right to their site, and they have links. Then you can get it as a Kindle book for about $35. This is $50. However, since most of you have Mathematica available, probably this free zip file, which has the chapters as individual notebooks but indexed so you can go back and forth, that's free from the Wolfram Media site. So you don't really have to pay for this. If you don't really want to tackle this whole 340-page document, there's a nice short version in the Mathematica Journal at mathematicajournal.com, and you can get that also in PDF, or better yet, in notebook form, and then you can manipulate it. So that's also available. If you do that and then you really want a chapter, I'll have individual notebooks on my own website, barryhdayton.space. And go to there. I already have a few corrections, and I will keep those notebooks up to date, and so on. Okay, they kind of left out an important word in the title here, that this book covers plane curves. I am working on the sequel to this, which will do space curves. But right now, you just have to go to my website to, if you want to see how far I've got. Again, I've got a summary, but it's only about half written. Okay, so an algebraic plane curve is it's the solution set of a polynomial equation like this one. It could have integers as coefficients, or it could have, in this case, these are really rational numbers as decimals, or it could be Mathematica machine numbers. And exactly what that solution space is something you have to read about, actually, in the Mathematica Journal version. This version, unfortunately, they actually left out that paragraph, unfortunately. But basically what we're saying is, if you use nsolve or find root, any output will give you a point on the curve. And so we can start out by, let's say, trying to, oops, no, that doesn't work here on this computer. Let's see, how about, no, that didn't work. Did the wrong thing. Oh, sorry about that. Okay, I'm not used to this. This is their computer. Yes. Okay. Okay, well, there's a little error here, but that's okay. Uh, okay, so what happened here, though, is I have this equation. Besides the polynomial itself, called f1, I put another little polynomial function in there and then solved these two simultaneously, and I got 7 points. Forget the stuff at the end here. We'll come back to those 7 points. So those are points on the curve. And this is the big difference between what I'm doing and, say, algebraic geometry, where curves don't actually have points because they're only allowed to use rational numbers as points, coordinates. But I can use floating point. I can use machine numbers. So we actually have points. Okay, and I can then. Oh, I know. What happened is I didn't get this first. Okay, let's go on to the next page. And then we'll be okay. Well, the next page, okay. The next page, I talk a little bit about what I mean by an infinite point. An infinite point is a triple that is the end of a line. And both ends of the line have the same infinite point. The first two coordinates of the triple give you the slope or the direction vector, and the third coordinate of an infinite point is 0. We'll see as we go on. Okay, let's try this again here. Okay, so let's see. Okay. I have a little general program which finds what I call critical points. And this is okay, what I really want to do with this polynomial f1 is I want to see what the graph looks like. I want to see what this looks like. Okay, that's what I want. That's my main goal. And basically what I'm going to do in this talk is give you 4 ways in which we can actually look at what this curve looks like once we also add the infinite points. So, okay, let's try this here. There we go. Okay, so here I have the so-called critical points. And, I need the infinite points. That was back 2 pages ago. Way down here. Yeah, again, okay, here we go. Oops. There, okay. I have to run this. Okay, there are infinite points right there. And notice they're triples ending in 0. Now let's go to where we were, and we get a nice picture of that. So we're going to actually make an association or a rule that will assign numbers to these various points so we can plot them nicely. And so there's my association. And now I'm going to go to the next page. And okay, so here's my contour plot. I can make a contour plot. Okay, so the critical points are numbered 1 through 7 in the black numbers. And you can see why I call them critical points, because they're kind of important points where this curve is turning. Actually, they're giving maximums or local maximum, local minimum of the distance of the points from the origin. These are not intrinsic points of the curve, but they are positional points. And then the orange numbers are the infinite points. So they're not where I put them, but they're at the end of those lines. And notice how the same point is at both ends. So both points called 9 are essentially, not quite, but essentially at the end of the x-axis, whereas the points marked 10 are essentially at both ends of the y-axis. And the points marked 8 are at the end of that kind of slanted line, which is parallel to the line x equals y, and so it has the same infinite points. Parallel lines meet at these infinite points. Okay, so my first representation is a graph in the sense of a graph in Mathematica. And, oops, no, there we go. Okay, so in this case, our graph consists of two cycles here. And if we look up here, the first one, say, starts with 0.6 up on the upper left, and then it goes to 0.9. Now, see, 9 is out here. So we start at 6, and then 9 is out infinite point next to 6. It's also the same 9 over there, so then it goes to 1, which goes to 8, and 8 goes to that other 8 up on top, which goes to 4. That goes to point 10, which is also the point at the bottom, and goes back to 6. So this graph gives that those connections. And then the graph at the bottom are those little black, those critical points in that little loop, which I guess you start with 2, and then you go to 7, and then you go to 5 and 3, and then back to 2. Now, any non-singular curve is actually going to, its graph is going to be a disjoint union of these cycles. And this gives us our what I call my fundamental theorem of plane projective curves, in that every projective plane curve can be fully described by a graph where the vertices are the critical and infinite points, and the edges correspond to an arc between the vertices. The key thing here is that every such graph is what's called an Euler graph. And an Euler graph is a graph where every vertex is even. That is, if you count the number of edges going in plus the number of edges going out, it's always an even number. Okay, that's the key thing. If it's a connected Euler graph, is known as an Eulerian graph. And that's a standard thing in graph theory. Now, if you have this graph, you can actually fill it out and get the curve by something called path tracing. I discussed that extensively in chapter 4 of the book. I don't have time to get into that. Conversely, if you don't know what the arcs are, but you do know the critical points and infinite points, then there are ways to try to figure out where the edges are. And it's a little bit slightly harder problem, but the book attempts to do that. Okay, my next representation is the idea of a hemisphere plot. Hemisphere plot, actually, if you Google it, is a standard representation of the projective plane. Basically, what I do is I use arctangent function to shrink the plane to the inside of a disk, in this case of radius 3r, and then the circle bounding that disk is the infinite line, and the interior is the normal, what we call affine plane. And then we can, a good way to see this is I'm going to plot on this hemisphere model a collection of lines, parallel lines of slope 3. And let's see what happens here. I get this picture, and you can kind of see why people might call it a hemisphere, although some of the people actually use actual hemispheres. But this is why it's called the hemisphere plot. And notice that all these lines go through the same infinite point, and that infinite point is, of course, at both ends of the plane. So that's here's another example of hemisphere plot. I have this curve, and if I take the contour plot, it's not very interesting. It looks like this. And it doesn't even appear that this plot satisfies my fundamental theorem, because it seems to have 4 different asymptotes that aren't connected, and that's not what my theorem says. It says that you're going to get an Euler graph that always comes around. If you follow any path, you'll get back to the beginning. But this is the hemisphere plot down below. And what we see in the hemisphere plot is, in fact, this curve has 2 infinites as tangent to the infinite line in 2 places. On the end of the x-axis, it actually hits the infinite line and comes back. In the y-axis, it's actually the infinite line is an inflection point. So it actually crosses it, but it's tangent to it. So the interesting part of this curve is at infinity. And that's a nice reason to have this model. Okay, the nicest model is what I call it's the Möbius band model. Again, this is a fairly standard model. See if I have here a Möbius band. To see how this works, here's a little Möbius band. What I do, well, it's easier to go backwards. So I pick, say, a little line which will be essentially my negative y-axis. I cut there, and then I follow this midline around the hemisphere, and then when I'm done, what I have is just a long strip. So the Möbius band is, so if you reverse that, what I just did, put it back together again, this long strip folds into the Möbius band. Okay, so the picture here, the ratio here between the 2 x and y axes is quite different, because it's supposed to be a very long skinny strip. But what we have here is the upper half plane is on one half, the lower half plane is the other half. We're kind of doing this by basically going to polar coordinates, and the infinite line actually goes around twice on the top. The whole bottom line, which corresponded with the original take another copy here, hasn't been mutilated. The whole boundary goes to 0, to the origin. So that all gets squashed to the origin. If you don't like that, you can think of the interior of this long strip as being the ordinary affine plane, but in polar coordinates, but bounded like in the hemisphere plot. And we're missing the origin. So if you take the plane without the origin, that gives you your affine Okay, your ordinary plane. Or you can actually think of this as being the projective plane with those tiny discs removed. There are various models you can use here. Okay, so here's some pictures of what this looks like. There's the first one, there's two lines, two parallel lines. They meet, that dotted line is the infinite line. They meet on the infinite line. A hyperbola has two infinite points, and so they connect on the infinite line. Three circles. The black circle goes around the origin, so it actually goes kind of all around the outside edge, so it goes around twice. But the other two don't, and so they're just kind of circular or oval shaped. And then the bottom one is the irrational function, and I drew each branch a different color, and you can see that we have two infinite points, one at the end of the x-axis and one at the end of the y-axis, and the purple ones go between those two, and the other, let's see if I can, no, I can't really do it here without a mouse. Oh, there we go. Well, no, this isn't without okay, well, anyway, I'm going to go on, but you can manipulate that. Okay, so the final thing, though, I have to tell you about our final representation. This is called a diamond diagram. And the diamond diagram comes in two varieties. One is the where we actually use the on the first quadrant, we actually take the sign of the coefficients, and if the sign is positive, it's a green point. If it's negative, it's a red point. And so the point at, say, ij is the sign of the x to the I, y to the j term. Then there are some ways of extending this to the whole picture, which is then supposed to be a picture of the whole projective plane with the x-axis, the y-axis, and the outside is the infinite axis. And basically this tells us that we can have one crossing of the y-axis. The curve could cross actually one or three times the positive x-axis. The negative y-axis can have 0 or 2 crossings, and there are going to be 0 or 2 infinite points in sort of the positive infinite line, which means the coordinates are the same sign, and we have to have 1 in the negative one. So this gives us actually quite a bit of information about the curve, and that's really just Descartes' rule of signs. Nothing more complicated than that. So that's useful. But the other representation with diamond diagrams is more an attempt to kind of model a region plot, but over the entire plane, including the infinite parts. And here it shows where the function itself is positive or negative. And unlike the first one, which just sort of constrains the curve, this is an actual representation of the curve. In other words, on the left-hand one, we see there the 3 positive components. The curve is going to cross the positive x-axis exactly twice. There's going to be one positive infinite point. There's going to be one negative infinite point, and it's going to cross the negative axis once. It's not going to cross the positive y-axis at all, but will cross the negative y-axis 3 times. So that gives us then sort of a representation of what this curve is going to do. So these are the ways that I can, once I figure out what this curve is, I can represent it in any one of these three ways or several of these three ways, and then I can understand what this curve is doing as a real projective curve. So, of course, if you want to find out more, you can get this book, or you can download the notebooks for free, either from my site or from the Wolfram site, Wolfram Media site, and you can find out all the details. So I think I'll stop here because my time's running out, and I know that's not the way we do it at this conference. We run over, but I will actually finish on time. So any questions? Thank you.